Okay, let's look at the cylinder problem in the midterm. So we had this cylinder that, well, this is an infinite cylinder, radius r, surface charge density sigma. It had an angular velocity omega. So there's a current on the surface of the cylinder, but inside the cylinder and outside the cylinder, we know that del dot B is equal to 0. Well, this is, in any way, it's always 0. The curl of B is equal to 0 inside and outside. Hence, in both regions, we can talk about, because the curl is 0, we can talk about scalar potential. Both inside and outside. So B would be minus the gradient of phi. Now, what else do we know about this phi? What can we say about this phi? Well, what can we say about B to start with? So our system is rotationally symmetric. That is one thing. And it is also translational symmetric along the z direction. Okay, so B, let's say its magnitude can at most depend on the distance from the central axis and on nothing else. We also know that the B should be, let's say, Bs in the z direction. Well, since it is in the z direction, and we know that, well, let's see. Now, B depends only on S. So what can we say about the phi? Can we say anything about the phi? You see, B is independent of Z, but that doesn't mean that phi is independent of Z. So that was in the hints. Now, what does it mean? You see, B, the Z component of B is minus d phi by dz. So phi can depend on Z, but its derivative should be independent of Z. So that kind of tells me that the phi can at most depend linearly on Z. That is the only option. So phi can be, phi m is phi 1, which can depend on S, times Z plus phi 2 of S. Now this is our separation of variable ansatz now. So let's continue. In cylindrical coordinates, Laplacian of phi would be 1 over S del phi m by del del by del S del phi m by del S plus d squared phi m by del z squared. This should be equal to 0. Well, phi m depends linearly on z, so the second derivative is 0 anyway. So this is also 0. So we know that 1 over S del over del S S del phi I by del S, both of them, should be equal to 0. Well, this tells me that S times d phi I by ds is a constant. Let's call it B. The derivative of phi I with respect to S should be B over S, or phi I, these functions phi I can be B times logarithm of, let's say, S over S0 plus C. Okay, just keep in mind S0 and C, they are not independent of each other. So by just redefining the value of S0, I can change the value of C. So here, although it seems as if there are 3 parameters, 3 constants over here, there are in fact 2 constants. One is B, the other one is C minus B logarithm of S0. Those are our 2 constants, 2 unknown constants. Or you can say that S0 is, just pick it up arbitrarily, then C is our constant. So So now we have phi m is, well, let me also put the labels bi and ci. Bi logarithm of s over s0 plus ci times z plus b2 logarithm of s over s0 plus c2. This is my most general solution, consistent with my symmetries. Now let's see, how do we determine these values? So we will have to have phi m inside my cylinder. Well, inside my cylinder, everything should be finite. So the logarithm term should be absent. So inside, I only have C1 plus C2. This is inside. Now, phi m outside, now I don't remember if we were already given the condition that B is constant outside. So since B is constant, or 0 in fact, then this should be a constant, just C2. Then the matching conditions. Well, we can always shift the value of phi so that we can set outside this to be 0 also. The matching conditions, we had two conditions. One, the perpendicular component of phi should be continuous. B perpendicular is continuous always. But this tells me that the phi m by ds is continuous. Well, if you take the derivative, b1 over s plus b2 times z, this should be equal to 0. Well, s is r. Well, this gives me a relation between b1 and b2. And the b parallel is discontinuous. And its discontinuity is proportional to the current density. The surface current density is omega r times sigma. So this gives you another condition. Well, the kind of the difficult part is to realize that the phi can have at most a linear dependence on z, and nothing more. So you don't need Bessel functions, you don't need any other functions. Yeah, you could have put enough phi dependence also in phi m. That wouldn't really change much. You could, in fact, have 1 over s squared d squared phi m by ds, the phi coordinate squared, if you didn't realize that the potential should be independent of the coordinate phi.
How is this 0?
Well, you see, because of this. You see, we know that B should be independent of Z. Okay? But if B is independent of Z, that doesn't mean that your potential is independent of Z. It can have this linear dependence. Well, I just use the fact that the potential, I look for a potential that is independent of phi though.
So we're not discussing the most general solution.
Most general condition consistent with our symmetries. Well, if you add the phi dependence of the solution, then you wouldn't have this equation, but you would have plus or minus m squared over s squared for the for the s dependent part of phi. And the solutions of this equation is s to the m plus over s to the m. But then when you use the discontinuity of the component of phi, then you will see that m should be 0, so all the a's and a prime should be 0. There cannot be any phi dependence. Now, I will upload the detailed solutions. Other questions? So I would rather continue with the electromagnetic waves in medium. Do you have any other questions about the midterm or anything else? So let's start with the electromagnetic waves in medium. First, I will discuss the dielectrics. Then we can continue discussing the conductors also. So how does we say that in electrostatics there cannot be an electric field in a conductor, but that doesn't hold anymore in electrodynamics because everything is changing with time. So we will see. So let's first rewrite our Maxwell's equations. Divergence of D in medium, this is equal to 4 pi rho. Curl of E, this is equal to 0. Divergence of B, now curl of E is not equal to 0. Curl of E is minus 1 over C del B by del T. Divergence of B is always 0. The curl of H is equal to 4 pi over C J plus 1 over C del D by del T. So these are the equations we have. And furthermore, we will be dealing with linear media. In linear media, we know that D is equal to epsilon times E, and B is equal to mu times H. Now, in conductors, when we study the conductors, we will also use the Ohm's law. The current at a given point is always proportional to the charge, electric field at that point, and the proportionality constant is what we call the conductivity. This is our Ohm's law. Well, I mean, is it the Ohm's law? Let's compare it with the familiar Ohm's law that V is equal to I times R. You see, if you have a conductor, there is an electric field here, and the potential difference, if you measure the potential difference, let's assume the electric field is uniform for simplicity. This is, let's say, length L. Potential difference is nothing but L times E. The current running through my system is, let's say this is a cross-section A. Assume the current density is uniformly distributed. I is just J times A. So V over I is equal to LE over JA. LE over J is sigma E times A. The E's cancel. V is equal to I times R, where R is just 1 over sigma L over A. This is the familiar Ohm's law you have, and the resistance expression. Now 1 over sigma is usually defined as rho resistivity. Not the charge density rho, but the resistivity rho. Now, if you have a conductor of an arbitrary shape, again, just the basic idea is the same. Just calculate the potential difference, calculate the current running through your system, and take their ratio. Their ratio is just your resistance.
always divide for any frequency? Because the electrons have mass, so they get compensated.
Well, electrons usually are moving very slowly. And this Ohm's law is, let's say, that is mainly valid for linear conductors. So J will be a function of electric field and also the frequency. I mean, if you have electric field is changing frequency, then this resistivity will depend on omega. There is nothing against that.
So that's only for high omega.
Not really for any omega. Even for small omega. I mean, omega is equal to 0 is our electrostatic case. Anyway, let's go back to our electromagnetic waves in medium in dielectrics. Now, if you just substitute these equations and express everything in terms of E and B. So these are the Maxwell's equations we have. Epsilon time divergence of E is equal to 0. Well, rho is equal to 0, J is equal to 0. I don't want any charges in my dielectric. So basically the question that we will be addressing is this window. Let's just look at a window. It's a dielectric. It doesn't have any free charges. There are no currents running through it. So how would the light behave in this window, in this glass? So that's the kind of problem we would like to study. So the divergence of E, even in this case, is 0 inside the window. And the curl of E is always 1 over C del B by del T. Del dot B is equal to 0. Now, H is B over mu. 1 over mu, curl of B. I'm assuming a homogeneous medium. So mu is just a constant. This is equal to plus 1 over C epsilon dE by dt. Or curl of B is equal to mu epsilon over C del E by del T. Well, let's see, what about the speed of light in our medium? How will it depend on, how will it change? Will it depend on this mu and epsilon? So let's look at that. Well, how did we obtain the wave equation from this? For example, we can just take the time derivative of the last expression. If we take the time derivative, curl of del B by del T is equal to mu epsilon over C del squared E by del T squared. But the time derivative of B is nothing but minus C, the curl of E, because of here. This is equal to mu epsilon over C del squared E by del T squared. Well, the curl of the electric field is minus C times the gradient of divergence of E minus the Laplacian of E is equal to mu epsilon over C del squared E by del T squared. Divergence of E is 0, and we are left with one over V squared del squared by del T squared minus the Laplacian acting on E. This is equal to 0, where V is just C over mu epsilon. Well, this is quite often defined as C over N being square root of mu epsilon. So this is the refractive index of a medium. And since mu and epsilon, it can depend on the frequency, so does the refractive index depend on the frequency. Well, most of the time mu is very close to 1. Its deviation from 1 is typically of the order of 10 to the power minus 4, 10 to the power minus 6. So this will be something like square root of epsilon, approximately. So it's mainly the dielectric constant that determines the refractive index of a medium. Well, this is not really that much interesting part of this. I mean, all the things that we had discussed last week about the electric waves in medium just applies over here. The only difference is that the speed is not c, but it's v, c over n. So with that replacement, all the results that we had obtained previously also holds here. And, v would be equal to omega over k in medium. And b was equal to k hat cross e for a plane wave. All of these will still hold. Because if you look at the equation, nothing has really changed in our equations. Well, where? No, B and E, they have the same units. And that K is not the K vector, but K hat. It's a unit vector without any units. So if you put a C, the units will not match. Now, let's look at reflection, refraction, etc. The interfaces. So basically, I will have this interface. On the left-hand side, I have a medium with refractive index N1. On the right-hand side, I have a medium with another refractive index N2. Now, to start with, I will just deal with the simple case where the electromagnetic wave, the K vector, is just perpendicular to the interface. So this is my K incident. They say this is my E, the incident electric field. What is the direction of P? Out of the screen. It's K times E. This is my incident wave. Now in the interface, some of it can just pass through. So here I will have K transmitted, E transmitted, and B transmitted, and some of it can be reflected. So I will have K reflected. Well, I don't really know what will happen to the electric field, whether it will stay in the same direction or not, but let's just assume that it stays in the same direction. If it doesn't stay in the same direction, I would just obtain a minus sign in front of the reflected electric field. What is the direction of B in this case? B changed direction. Again, as I said, I don't really know whether B changes direction or not, or E changes direction or not. I know that one of them should change its direction because K changes direction. Now, if it is the electric field that changes direction rather than the B field, then I know that the E reflected should be minus a constant times E incident. So that is what I will be trying to find. What about, and let me also just make this identification, EX, E incident will be E incident 0 e to power I kx or kr minus omega t. E transmitted will be E transmitted 0 e to the power I k dot r minus omega t. And E reflected 0 e to the power I minus k reflected, or k reflected dot r minus omega t. This is k transmitted, this is k incident, and k reflected is minus k incident. So these, with the zeros, I have the magnitude. So what I will try to find is kind of find relation between E transmitted and E incident, and E reflected and E incident. So what are these constants appearing over here? That is what I will be trying to find. Omega. Well, you see, what is omega? I mean, we want to find, how will we find these relations? We will basically use the boundary conditions. We will use that the parallel and perpendicular components are continuous at all times. Now, if omega are different, in that case, I know that even if they are continuous at a given time, since they will change differently in different medium, that continuity will not hold anymore after some time, if omega are different. So that's why omega has to be the same. Convinced? Let's look at our conditions, and then we can see what will happen. Now, what about the continuity conditions we have? Divergence of D is equal to 0. Well, this tells me that the perp is continuous. Well, the perp is just epsilon times E perp is continuous. This is one condition I have. Curl of E is equal to minus del B by del T. Well, this tells me that E parallel is continuous. Del dot B is equal to 0, which tells me that B perpendicular is continuous. And curl of H is equal to, I have 1 over C del D by del T, which tells me that H parallel is continuous, or B over mu, B parallel over mu is continuous. So these are the conditions that my waves should satisfy at all times, at every point and on the interface. Now let's try to impose those conditions. Well, you see, I don't have any perpendicular component. All the components are parallel because I'm assuming K is perpendicular to my surface, so both E and B, they are perpendicular, they are parallel to my interface. So K is perpendicular to the surface, which tells me that B parallel, B perpendicular is 0, E perpendicular is 0. Everywhere. So I don't really have any conditions on this. Doesn't give me a new condition, this doesn't give me a new condition. I only have two conditions. The parallel component of the electric field should be continuous. Well, the electric field is only parallel, so the electric field is continuous across my interface. So that tells me that E 0 incident e to the power I k incident dot r minus omega t plus E reflected 0 e to power I k reflected dot r minus omega t should be equal to E transmitted e to power I k transmitted dot r minus omega t. Because if omega in each one of these terms were different, then even if I satisfy this equation at some particular time, I cannot satisfy it at a different time. So this equation already tells me that all the omegas should be the same. Now, k is in the, I mean, if you just choose the plane xy as the z is equal to 0 plane, that is your xy plane, the interface, then k is in the z direction. And k dot r, whether you are talking about k incident or k reflected, is just k times the z coordinate. But on the interface, z is already 0. So k in that, on the interface, k in dot r is equal to k reflected dot r, which is equal to k transmitted dot r, and they are all 0. If we choose the xy plane on the interface. Well, if it is not, I mean, in the case when the plane wave is not perpendicular to the surface, well, it will not be necessarily equal to 0, but nevertheless they should all be equal to each other. And this would give us the Snell's law of refraction. That we will discuss later on. But in this case, we are moving perpendicular to the plane. K dot r is equal to k times z, but z is equal to 0. So that's why all of them are 0. So our equation for the electric field is actually incident 0 plus E reflected 0 should be equal to E transmitted 0. This is one condition we have. Now let's look at the other condition. You see, the other condition, the continuity condition, is B parallel, or that's actually our B, divided by mu is continuous. You see, we know that B is nothing but k hat cross E divided by mu. This should be continuous. But this tells me that E over mu is continuous. Not just E, but E over mu should also be continuous. Do you agree? No, K is not. That's K hat. No, K hat is nothing but the Z axis, Z hat. So let's see. This basically tells me that E in 0 plus E reflected one over mu mu2, mu1, mu2. Do you agree? I don't. K hat is not the same for all the waves. Because K hat is the same for incident wave, for the transmitted wave, they are both moving in the same direction, but K hat for the reflected wave is in the opposite direction. So that is why I have that minus sign in between the incident and reflected waves. So let's see, this is my second equation. How many unknowns do I have? I just have two unknowns. I don't know the reflected wave, I don't know the transmitted wave. Furthermore, although I'm using the vector notation over here, the vectors have three components. I already started by choosing one plane, so everything is in that plane. So the only thing that is not known is one component of these waves. So basically I have two unknown coefficients. Now let's see. So 1 over mu1, E incident 0, minus 1 over mu1, E reflected 0. This is equal to 1 over mu1, E incident, plus 1 over mu1, E transmitted. No, reflected, sorry. I just used the previous condition on my waves. So now I can solve for the reflected wave. All right, this is mu2. 1 over mu1 minus 1 over mu2. E incident is equal to 1 over mu1 plus 1 over mu2. E reflected, or the E reflected is equal to mu2 minus mu1 divided by mu2 plus mu1, E incident.
Shouldn't we expect that epsilon dependency?
What happened to the epsilon dependency? You see, epsilon dependency comes in two places. In this equation, but you see, the perpendicular is continuous, but the perpendicular is 0 anyway. So epsilon dependency just disappears from that equation. Now, another epsilon dependency comes from this equation. But again, this equation doesn't, it just tells me that H parallel is continuous. Now, the epsilon dependency, you see, how do I obtain the H parallel to be continuous? I just took, this is my interface, I assume such a small loop, integrated both sides over this area. The left-hand side becomes the loop integral. The integral of the curl of a vector field over an area is nothing but the integral of the vector field around the boundary of the loop. Now the right-hand side, it gives me the flux, but then I set this length to 0. So that flux just disappears. So again, the continuity condition, the boundary conditions do not depend on D, and hence it doesn't depend on epsilon. But that doesn't mean that there is, here there is no dependence on epsilon. But I agree with you, it's just weird. I would also expect an epsilon dependence somehow. I would expect, rather than having mu2 and mu1, I would expect to have some dependence on the speed.
What you said?
Hmm?
You said it depends on the frequency. Usually more,
Sure.
which affects the speed.
Yeah, I mean, indirectly, of course, there will be many dependencies, etc. But I agree with you, no epsilon dependence, not weird. But I can also see why there is no epsilon dependence from the equations, at least. Now the transmitted wave, well, we can just use this relation, mu2 minus mu1 divided by mu2 plus mu1 plus 1 E incident, which is equal to twice mu2 divided by mu2 plus mu1 E incident. So you see, transmitted wave is always in the same direction as the incident wave. Well, the reflected wave, it depends. It can be in the same direction or it can be in the opposite direction. So here I always have these zeros. These are the amplitudes. Now, when the wave is not perpendicular to the interface, then we will have some epsilon dependencies. Any questions on this? Well, here we will, you will have to think in 3 dimensions. This is our interface. This is K in. This is K reflected. This is K transmitted. Let's call it theta incident, theta reflected. This is theta transmitted. Now we will be separating 2 different cases. You see, this is our interface. This is my K. This is my E. This is my B. Okay. Now, when we make this, there's an angle. When K makes an angle with the interface, it is possible that B still stays parallel. E is no longer parallel. Or it is B, E is parallel, but B is no longer parallel. Well, any other combination, both of them might lose their parallel components. We can always separate it into 2 components in which in one of them B is parallel, in the other one is the E that is parallel. Try to visualize it. So we have to study these 2 cases separately. Now first let's write this condition. Now this condition will still hold. when we were writing this condition, well, this was the, let's say, the parallel component. This is the continuity of the parallel component. You see, let's go back. So these are our conditions. And in deriving these conditions, we didn't use anything we didn't even make any assumption that E and B, they are part of a plane wave. These conditions should always hold. And so E parallel is always continuous. So this condition over here for the parallel components of the electric field should always hold at every point on the interface at all times. Now, one condition that we obtain from this is that omega should be the same, since this condition holds at every time. The other condition, since this condition should hold at every point on the interface, K incident dot R should be equal to K reflected dot R should be equal to K transmitted dot R at every point on the interface. So let's just pick up any point on the interface, some point R. Now this condition tells me that magnitude of K incident times the magnitude of R times cosine of the angle between the two. They say this angle, pi over 2 plus theta I, plus K reflected is its magnitude times R times the angle between the two. It is this angle over here. It is pi over 2 plus theta R. Should be equal to K transmitted times R times cosine of pi over 2 plus theta transmitted. Well, R is the same in all of them. And remember, K incident, the magnitudes, are just V over omega. Or V is just C over N omega. And if we just substitute over there, well, C over omega is just common in all of them. So that tells me that 1 over N incident times minus sine theta I plus 1 over N incident minus sine theta R should be equal to 1 over N reflected minus sine theta transmitted. Okay, this is one condition we have. Sorry. What am I talking about here? These are equal, not plus. Sine of theta transmitted divided by n transmitted, or n1, n2, n1, and n2.
How do we justify the second equation?
Which one?
Sine theta of k transmitted equals to k incident.
This condition. You see, I have the sum of these three complex numbers, and they should hold at any value of r and at any value of t. If they are to hold at any value of r and any value of t, I should be able to cancel the r and t dependencies on both sides. So those exponentials have to be the same. So that's how I get this condition. So I just wrote the scalar products in terms of the product of the magnitudes and the angles between them. That gives me these three equations. But r is the same, and instead of the k is omega over v. Or omega over c times n. Okay. This is n1, this is n1, this is n2. Incident wave and the reflected wave are in the region with refractive index n1. Transmitted wave is in the region which has a refractive index n2. So basically these equations tell me that the angle of incidence and the angle of reflection has to be the same. And furthermore, n1 times sine theta incident should be equal to n2 times sine theta transmitted. And this is our Snell's law. Well, the Snell's law basically tells us that these phases should be equal.
Experimental numbers handle phosphorus levels. All elements. We tend to have a structure.
No? This holds for any angle.
That axial approximation. The axial approximation holds for one. So when you say sine theta is equal to theta, that's all.
No, this is always valid. Again, up to this point, we didn't really make any assumption about how the wave arrives at our interface. The only thing we assumed is that if these continuity conditions are to hold at any time and at any point on this planar interface, in that case, the phases should be equal, and if the phases are to be equal, we have this law. Well, there's still, in a sense, we are making several approximations here. One thing is we are using the plane wave approximation. We are assuming an infinite wave. But you see, and if you have a finite wave, you need to make superposition of these waves. And if you make a superposition of these waves, they will probably have different frequencies. If they have different frequencies, n values will be different for different frequencies. So So that is where one approximation in this law is.
And then, so what do we need plane waves for this,
Hmm?
for this data? Where do we assume plane waves?
Starting from the beginning, I mean, these phases are the phases of plane waves. You see, in a realistic situation, let's say, this glass over here, you shine some wave over there, okay? Now, it will not be a plane wave, I mean, if you use the laser. It will not be a plane wave, it will be a superposition of various waves. Not just a single plane wave. So, the source will not create really a real plane wave. That is one approximation we are making. Now, is it related with making a small angle approximation? I mean, I will still stick with this law. You see, under which circumstances the plane wave approximation can fail? If you can sense the long distances, for example, one case is you have this planar wavefront arriving. Suppose it is tilted like this. Well, I mean, you have to take the finite size of this thing into account if you want to describe such a case. Okay. So if you have if you have an infinite plane wave which is not perpendicular, some part of the plane wave will hit earlier than the other part. So that might be one thing where we might be assuming small incidence. So if that part that hits the surface is very, very far away, in that case, it won't have any effect. You see, the phenomena that we are assuming over here is there is this incident wave. Yeah, it is hitting it at some point all the time. But in real life, you will have such waves. This is what we would get in real life. Now, somehow, the neglect of these parts shouldn't change whatever is happening. Well, the neglect of that part wouldn't affect what is happening if this point is very, very far away. But that point is very, very far away if the angle of incidence is small.
You understand what's the effect of that point?
Of that point?
I mean, what's the problem? We have even infinitesimally small wave.
You mean this wave?
Yes.
Well, if you have such a wave front, then you will have problems. That's for sure.
Why?
Why? Because this is a superposition of many, many, many plane waves. I mean, you see, if you have you seen the uncertainty principle? Okay. Delta K, delta X should be larger than or equal to 1 over 2. This is true for waves, any wave phenomena, even classical waves. So you see, here you have a very small wave. So delta X is very small. So delta K should be very large. So you need to add plane waves having many, many different wave numbers. But that means you need to add plane waves with many different frequencies. And if you are adding waves with many different frequencies, every frequency will refract in a different way, because n in general depends on the frequency. That is not something what you want.
And how does perpendicular incidence or near perpendicular incidence fix it?
Near perpendicular incidence. Well, there is no refraction. So there is no Snell's law anyway, for any frequency. Now, there is Snell's law, it's 0 equal to 0.
That's why I said near. That's why I said near.
Oh, near one. Well, to be honest, I don't know. What I'm saying is, are we making a small angle approximation somewhere?
If it's a
we are approximating a real life case which has a finite width light with the ideal case which has an infinite width light. So the question is, under which circumstances can we do this approximation? So that's kind of the question. Yeah, we can do this approximation if the angle is small angle incidence. Because in that case, well, you see, this is small compared to what? So we have to compare it with something. Or that should be large compared to what? I would say compared to this length. But that means this angle should be small. So what goes wrong if that angle is not small? I don't really know. I don't have a definite answer.
One thing we stop. Here, when we say delta K, K has a direction. Right, so it should be in the direction of X. Yes. So, which means that it shouldn't affect our K direction. And this uncertainty principle does not affect it.
Yeah, you see, K is constrained. The magnitude of K is fixed by the frequency and the velocity. So if you put additional constraints on the X and the Y and the Z components, they also influence other components because the total magnitude is fixed. Or let's say, if you set, I don't know, let's say delta Kx is very large, then the magnitude K should be very large. The range of values of K should be very large. If the range of values of K is very large, then omega should be, the range of values of omega is large. Do you want to break? We have half an hour left. If we give a break, it should be 5 minutes. Do you want to break? No. Okay. At least let's just do the analysis of one case where we will have a perpendicular is 0. This was the first case. The perpendicular component of the electric field is 0. So we will be only looking at the electric field will be perpendicular, or if you have this example, this is K, this is E, this is B. So we are looking at such a case. The wave is approaching such that the E is parallel. So this condition over here, well, still holds. We have E incident 0 plus E reflected 0, E transmitted 0. No change in this. Let's go back to our continued conditions. E parallel is continuous. Okay, that is the condition we have. E perpendicular is continuous. Well, there's no E perpendicular in our case, so there's no condition from this law. B perpendicular is continuous, so we have these additional laws, constraints on our system. Well, B perpendicular, there is B is k hat cross E. That is how we relate k and E. So B perpendicular is continuous. K cross E incident minus K cross E K hat cross E reflected. Take the perpendicular component. This should be equal to K cross E transmitted. Take the perpendicular component. And the parallel is continuous, tells me that 1 over mu 1, K cross E incident, minus 1 over mu 2, K cross E transmitted, should be equal to, take the parallel component, should be equal to 1 over mu 2, no, this is mu 1, cross, now K hat cross E, now these are all K hats, transmitted, take the parallel component. These are the two additional conditions I have. Well, the relative minus sign over here is due to the fact that the k vector for the reflected wave is minus the k vector. Oh, sorry, no. This is completely wrong. You see, the k vectors, now they are completely different vectors. It's not just the change in the sign or the change in direction, etc. They're completely different. Now we have to solve these equations. Now, this is the case we are studying. This is our interface. This is K incident. This is K reflected. We already know that their angles are the same. And this is K transmitted. Let us show the B vectors, not the E vectors. Let us assume that the E vector is into the screen. So this is E incident, 0. Then the B vector is in which direction? This is K cross E down. This is B incident, 0. And so here this is K reflected. Let's assume that E reflected is still in the same direction. So this is B reflected. And in the transmitted wave, let's also assume that E transmitted is in the same direction. So B reflected is in this direction. No, transmitted. Or let us just show all the B vectors at this point. This is B incident. This is B reflected. And B transmitted is somewhere like this. Now what are the angles they make with the plane? Let's start with reflected wave. Well, it should be either theta incident or minus. It should be either theta incident or pi over 2 minus theta incident. Just look at here. Hmm?
Daha da kalem verebilirsiniz.
Now I will just draw it again. So this is my interface. This is my K reflected. This is my B reflected. This is the perpendicular axis. These are perpendicular to each other. This angle is theta incident. So this angle over here is also theta incident. Do you agree? So this angle is theta E. Well, this angle is also theta E. Just use the same reasoning. Let's be sure. So this is my K incident. This is my B incident. These are perpendicular to each other. So this is my theta E. This is my theta E. And for the transmitted, this is my theta transmitted. Which one? Theta E. This is the second one here. Reflected lemma. Okay, so do you agree that this is our theta E? It is the K reflected makes with the vertical. Well, this angle over here is pi over 2 minus theta E. So the angle between the B reflected and the surface is theta E. Now let's go back to our conditions. We have B perpendicular is continuous. And now before continuing, keep in mind that the magnitude of B is equal to K hat cross E. So the magnitude of B is equal to the magnitude of E because they're all perpendicular to each other. So the conditions we have, B perpendicular is continuous. The perpendicular component of B. We have the incident B. The perpendicular component is E incident times sine theta E. Plus we have the reflected B, E reflected times sine theta E should be equal to the transmitted B, the perpendicular component, so E transmitted times sine theta T. Well, I'm talking about the perpendicular component of B, but keep in mind that the magnitude of B is equal to the magnitude of E. So that's why instead of the magnitude of B, I put the magnitude of E. Now the second condition is B parallel over mu is continuous. Are we correct in the directions, by the way? Let me check. No, okay. Now the parallel component of B is continuous. So from the incident we have E incident 0 times cosine theta E over mu1. We have the parallel component of the reflected B, that is minus E reflected times cosine theta E over mu1. This should be equal to E transmitted over mu2 times cosine theta transmitted. And then we had one more condition, this one. E incident let's say E's are always in the same direction, plus E transmitted, no, E reflected should be equal to E transmitted. Well, there seems to be one problem though. We have 3 equations but 2 unknowns. So either 2 of these equations are independent, the third one depends on the other one, or we will run into a problem. So let's try to solve the first 2. So we already know theta incident is given, transmitted theta we already know from the Snell's law. So the unknowns are E transmitted and the reflected amplitudes. These are the things that we do not know. Okay, so we have time to solve for them. Well, let's solve these 2 equations. They will be easier to solve probably. So we have E incident cosine theta I incident angle 1 over mu1 minus 1 over mu1 E reflected cosine theta I. This should be equal to E transmitted, which is E incident plus E reflected times cosine theta transmitted 1 over mu2. One over mu1 cosine theta I minus 1 over mu2 cosine theta t times E incident. This should be equal to 1 over mu1 cosine theta I plus 1 over mu2 cosine theta t times E reflected. So we know E reflected. Yeah, this is transmitted. So we know how much of the wave will be reflected. Now the transmitted is just E reflected plus E incident. And this just gives us 2 over mu1 cosine theta I divided by 1 over mu1 cosine theta I minus 1 over mu2 cosine theta t in incident. Now, we have the problem. Or do we have the problem? We already know the reflected and the transmitted amplitudes. Do we satisfy the first equation? It should also be satisfied. So let's check whether our solutions satisfy this equation. E incident 0 sine theta I plus the reflected, we had calculated it, this one, 1 over mu1 cosine theta I minus 1 over mu2 cosine theta t divided by 1 over mu1 cosine theta I plus 1 over mu2 cosine theta t sine of theta I times E incident. Is this equal to E transmitted? We also know E transmitted. Two over mu1 cosine theta I over 1 over mu1 cosine theta I plus 1 over mu2 cosine theta t times E incident sine theta t. Will this be satisfied? Let's see. Let me just multiply with 1 over mu1 cosine theta I plus 1 over mu2 cosine theta t, etc. Sine theta I times 1 over mu1 cosine theta I plus 1 over mu2 cosine theta t. This is the first term. The second term is basically the same thing with a minus sign. This is the second term. Should be equal to, is it 2 over mu1 sine theta t times cosine theta I. Well, this term will cancel this one. So the question is 2 over mu1 sine theta I cosine theta I. Now these are t's. Is this equal to 2 over mu1 sine theta t cosine theta I? Sine theta t. So what is wrong? So is it 2 mu1s we can cancel, cosine theta i's we can cancel. This gives us sine theta I is equal to sine theta t. So we did something wrong somewhere. So, yeah, I mean, if theta is equal to 90 degrees, it is true. Then theta t is also 90 degrees. Or if both are 0, it's also true. Well, if theta I is 90 degrees, then theta t, they don't both need to be 90 degrees. Remember the Snell's law? They don't need to be 90 degrees at the same time, but they have to be 0 at the same time. If they are 0, this holds, but that's not what we are interested in. So we did something wrong, definitely. Let's go back. Now, we can always assume that E is parallel. There's nothing that can go wrong over there. Now, E parallel is always continuous anyway, because curl of E is equal to minus the derivative of B, from which we can always derive the condition that the parallel component of E is always continuous. So there is nothing wrong with this equation. So to solve this equation at every point, this has to be true all the time. This gives us the Snell's law. So that's nice. So if the perpendicular component is 0, then the parallel components is not, the electric field is only has the parallel component, so this is correct. So there's no problem with this law. Now we know that B perpendicular and B parallel over mu, they should both be continuous, and B is K cross E all the time. So the directions of B's, if E is always in the same direction, then if K changes sign, B should change direction. So that's kind of, the directions of B's are also fine, correct, here. The identification of the angles. Are they correct? Well, they should be. If, let's say, if theta incident was 0 degrees, then B incident and reflected B's would have been parallel to the surface, so they should have been, no, hold on. If theta is 0 degrees, then B's should be parallel to the surface, so those angles should be also 0 degrees. If the incident angle is 90 degrees, then B's are always perpendicular to the surface, so they should also be 90 degrees. So the identification of the angles also seem to be correct. Mm-hmm. Theta transmitted, that is correct. Hmm? Now the angle that B transmitted makes with the surface should be related with theta transmitted. So that angle, I mean, of course theta transmitted is related to theta incident, but that angle is related only with theta transmitted. So the identification of the angles are also correct. This angle?
Yes.
Oh, why do you care? Hmm? No, not necessarily. You see, beta incident and beta reflected, they are both perpendicular to K. K incident and K reflected. So if K incident and K reflected, they are at 90 degrees, only in that case, beta B incident and B reflected, they make 90 degrees with each other. So there doesn't seem to be any problem with the identification of the angles. Well, in this one, there wouldn't be any problem. B is always K cross E in medium and in empty space, in space where there are no charges, etc. If we are talking about plane waves, then B is always K cross E. So let's see, K cross E. Yep. So perpendicular component of B is continuous. The perpendicular component is given by the signs. And they are all pointing in the same direction. So there are no relative minus signs. B parallel over mu is continuous, but they are So if you write the downward components of B parallel as positive components, so E incident, B reflected has a negative contribution. So this equation is also correct. So we solve the last two equations. Let's see, E incident So there is this minus sign, E reflected, comes with a plus sign. Let's see, mu2 is cosine theta transmitted. So E reflected has this relation. Let's see. Well, that doesn't seem to be a problem there. Now E transmitted will be just E reflected plus this one. Hold on, this is a plus sign over here. So this is a plus sign over here. So if we just add E reflected, E incident to this one, cosine theta t terms cancel, we end up having this term. So this is theta t. And then we are checking this relation. Which doesn't hold. So that's at least in our derivation, nothing seems to be wrong. So maybe in our conditions we have some problem. And there'll be a problem over here. So what is it that we might be missing? So what would you propose? What should we check?
Well, we got three equations.
Mm-hmm.
Because we need two of them, since we have two numbers. And one tells us.
Well, the problem is we know the angles, and in terms of the amplitudes of these plane waves, we have three conditions. Well, this condition doesn't really give us anything because E perpendicular is already 0 on both sides of the interface. So we have three conditions, one from the continuity of E parallel, one from the continuity of P perpendicular component of P, and one from the continuity of the parallel component of P over mu. But we only have two unknowns. Or do we really have two unknowns?
You shouldn't really answer two unknowns.
Well, let's see, this is our K. We are bending it something like this. So actually, well, the E has one component, so we can choose this direction. K is fixed, B is fixed, so E is fixed, K is fixed already. At least the direction of E is fixed. The magnitude is one unknown. And then B is fixed. There is no freedom in B. Both its direction and magnitude is fixed. So we do have one unknown for the reflected wave and one unknown for the transmitted wave. So that gives us two unknowns. But we have three equations. Either one of those equations are not really correct, or these three equations are not all independent.
Then they shouldn't contradict each other.
They should not contradict each other.
Since they contradict each other.
Then that definitely we are doing something wrong. What are we doing wrong? Hopefully we will find by Wednesday. Okay, I understand that kind of the derivations are boring. It's something that you have to do once in your lifetime. So we have this one. We have the case in which the B will be parallel to the plane of the interface. We also need to study that case. And after that one, we will look at what happens if we have a conductor. We will see that when we have conductors, the electric field can in fact penetrate the conductor up to some length. And then that will be kind of all of it about electromagnetic waves. And then we will start, what about the electromagnetic field created by a moving charge? Not necessarily moving slowly. And that will be the end of the semester. Okay, so see you on Wednesday.